Okay, so today's final topic of the semester on computational methods in fracture mechanics. I'll give you first, before we dive into the computational methods, a brief overview and survey of what you need to know from fracture mechanics, a very brief introduction, and then we'll dive into the actual computational aspects of how do you represent and model fracture in a practical setting. But I will also point out that if you do want to get more of a technical and theoretical background and understanding of fracture and how it fits into the domain of engineering analysis, I'll point out there's plenty of resources online, some of which I've also presented in a previous course. So last semester, I had a couple of lectures that touched on this particular subject of fracture mechanics, providing mostly an introduction to linear elastic fracture mechanics. So some of those details are actually slightly orthogonal to what we'll talk about today, which is the slightly more general, conditions of assessing when does fracture occur, not just under assumed linear elastic conditions, but under more general conditions where you might have nonlinear material behavior. And at that point, it becomes a little bit more difficult to assess when fracture occurs. So nonetheless, it's a good background introduction if you want to take a look. I'll leave that up to you, though. I assume no prior knowledge, however, so we'll kind of proceed as assuming that you haven't participated in that previous class. Okay, so let's talk about fracture. And I almost hesitated to include this slide because I assume you all know what fracture is. But just to clarify what we mean by fracture, it's really just a definition of what happens when material breaks apart. So imagine in a simple example, I have some uniaxial bar placed into a state of tension. And for the sake of this example, suppose that this loading that I apply to this uniaxial bar is displacement controlled. So rather than applying some fixed force to the end of this bar, imagine instead that I have some clamp that allows me to tug on the end of this bar and control the displacement. So regardless of what the resulting force is in this bar, what I'm controlling is the displacements. All right, so I can certainly take the end of this bar, do a displacement controlled test or something like that, maybe in a uniaxial testing environment. I can extend it by some finite amount, which I'll call U with a bar over it, and it'll kind of grow by some finite amount with some internal state of strain in it, perhaps. And let's say that this bar behaves in a somewhat brittle fashion, in the sense that I might continue to load this bar up, and the relationship initially will look like there's a linear correlation between the applied force and this imposed controlled displacement. So very much as we would expect to see in any kind of simple linear elastic uniaxial tensile test, until, let's say, at a critical point where I stretch this bar out to this critical value, all of a sudden, bam, the test ends because the material breaks apart. Some fracture or some crack forms interior to the specimen. And in the process, we also notice that on this force versus deflection diagram, at the point of fracture, given the fact that we're using a displacement controlled test, rather than unloading the material elastically back down this initial slope, if we've kind of fixed the displacement at this value of U bar at the point of failure, what we'll see is that the displacement will be the same right at the point of fracture, but certainly the applied load carried in the specimen will drop down to zero. So that's kind of what we'll see. We'll see there's some internal strain energy, basically, contained underneath this curve that was originally stored internal to this bar when we stretched it out. But then when it got to this critical loading value, let's call that, F, the critical loading value, F sub F, or the critical load at failure. At that load, we drop down to zero force. Okay, and it's kind of interesting that we go from this state of, stored elastic strain energy in this bar, and then instantaneously, seemingly, it'll drop down to this state of zero force. So it's almost like whatever internal strain energy was stored in this bar previously, after fracture occurs, it just goes away. We lose all the internal strain energy. So where did it go? Did we just lose it? We misplaced our strain energy? That's the thing that we really need to observe about fracture is effectively whenever we introduce some kind of mechanism for damage, we lose energy in the process of introducing whatever damage into this particular specimen, let's say. So effectively, the interesting aspect of this is that obviously, besides the fact that we have this loss of load carrying capacity, we're also introducing some new internal surfaces in the specimen, right? Where there was no crack here before, now there's like these two open interfaces and we've split the bar in two. So fundamentally, we've changed the topological structure of this bar. What was originally one continuous piece of material is now two separated pieces of material. So a few different observations that we can take away from this very fundamental kind of study. But I think the thing that's worth looking at is that even if we took that perspective of this bar and we said all we really looked at was macroscopically what happens to the bar. Originally one bar, then it split in two. Originally it could carry load, now it can't carry any loads. It's worthwhile to actually take a slightly more zoomed in perspective of what's going on internal to this chunk of material when it actually undergoes this fracture process, when those surfaces split apart and create two new, fracture interfaces. So one way to investigate this is to certainly, do some kind of macroscopic examination of how do cracks not just form instantaneously, but how do they grow? Perhaps in a slowly controlled environment where maybe I have a specialized test specimen, sometimes called a compact tension specimen, that is specifically designed so that I can control this, displacement of these kind of anchors here shown in the blue crosshatch. And if I control them slowly enough, then I can actually very slowly grow some initial crack that might have been placed internal to the specimen. So if I control that rate of extension of these loading arms, then I can slowly see what happens as I extend some initial crack. And I can look at not only what's happening at the macroscopic scale, what I would see if I were to go into the lab and run the experiment. Certainly I could see there's an initial crack and maybe it'll grow by a little bit, but it's also worth looking at what's happening at smaller scales in the material. Not just what's happening at the macro scale, but also at mesoscales, sort of these intermediate scales that might be at the scale of individual grains or grain boundaries in, let's say, a polycrystalline metal. Or maybe it's at the level of, individual aggregates or sand particles in some kind of inhomogeneous, cementitious composite like concrete. And at those scales, a lot of interesting features can show up, a lot of interesting inhomogeneities in the material, which can introduce nuanced behaviors of what's happening in the vicinity of this crack tip location. And then we could take an even closer look. We could zoom all the way down to the level of the individual atoms in this, packing of material at the atomic scale. We can notice that, obviously at the lowest scales of interest, we're looking at atoms that are bonded together. And that's kind of originally what you might think of as the material as being contiguous. It's just a collection of atoms that are actually bonded. Now, if we actually ran this experiment, increased the amount of displacement on this specimen, what we would notice is that certainly from the macroscopic perspective, the crack, which had initial length A, might grow by some small amount, which I'll call delta A. But it certainly, in this controlled setting, doesn't grow all the way through the specimen. So clearly we see that, crack extension can be controlled depending on the nature of how you're applying the loading to the specimen. It's not an instantaneous thing all the time. But what's more interesting is that besides the fact that certainly from the macroscopic perspective, the crack has extended, but also if we take a closer look at what's happening in the local vicinity of the crack tip location, at the mesoscale, we can see a ton of interesting phenomena going on. And really, it's not as simple as saying that there's a crack here or there isn't a crack here. Really, there's a whole sequence of different localized damage processes and plasticity that can happen in the vicinity of this crack tip at these smaller scales in the material. And within this kind of localized region, just ahead of the crack tip, You might have some plasticity due to very high concentrations of stresses in the local vicinity of the crack tip. And as you continue to load the material in the vicinity of this crack tip, various other things can start to happen. Small micro cracks can form within this kind of advanced location in front of the crack tip. And those small micro cracks can grow into micro voids. And those can grow until eventually you have further extension of the actual crack itself. So the important thing to note here is that really, fracture doesn't just happen in this instantaneous fashion. It happens through a process of different steps. And it really starts from, plasticity to microcracking to, microvoid growth and then void coalescence. But really at the smallest scales, it is still characteristic of bonds breaking in the material. So that's kind of the indication that obviously once the material fully separates, well, that's technically what we call fracture. But really at the mesoscale, there's a bunch of details that account for these mechanisms that govern fracture. And the thing that I really want to point out in this diagram is that, in observation of the things that we talked about on the previous slide, when we had this bar, we stretched it out. There was some internal elastic strain energy in the bar. And then all of a sudden, when it fractured, it seemed like we lost all that energy. So where did it go? Well, it takes energy to actually generate new fractured interfaces. And that energy is dissipated both through the breaking of these bonds at the atomic scale, as well as through all of these dissipative local damage and plasticity processes within this so-called fracture process zone in the material. So damage and basically mechanical energy dissipation is happening through both of these different processes at multiple length scales in the material. And that is precisely where that energy goes. So we lose mechanical energy in order to basically develop these local damage processes and advance the crack front. But it really does require acknowledging that things are happening at fine scales in the material, all the way down to the atomic scale. So it's an inherently multi-scale process, but nonetheless, we can still carry out some rough coarsened analyses that just look at, well, we know that energy gets dissipated to generate these fractured interfaces. So can we say something about the amount of required energy in order to generate new fractured interfaces or to advance this crack front? And that's precisely how very common descriptions of failure criteria or fracture criteria are specified. So going back to the same problem and acknowledging the fact that really, if we went from a state of unfractured bar in this extended state to now a fractured state, dropping from whatever applied load down to zero load, then in the process of dropping down to zero load, we will dissipate energy. And the amount of energy we dissipate, at least for this uniaxial bar, is directly proportional to the area under this force versus displacement curve. So this area, you can think of it as the energy that went into generating this new fractured surface in the material, this kind of new fractured location in the bar. And if I wanted to, I could also say, let's normalize it by the actual surface area that was generated. And if we do this, we can define a new quantity, which is sometimes called the fracture energy. In other contexts, you might hear it as the critical strain energy release rate. But it effectively says, this is the amount of energy per unit of surface area that I need to put into the material in order to generate some new fractured interface. So I have to do mechanical work, and this is the amount of work per unit of area required to generate some new fractured surface. So again, it has units of energy per unit of surface area, and specifically where that surface area is a unit of crack surface area. So if I want to generate energy, I have to put in this amount of energy to generate some crack or to extend it by some infinitesimal amount. And this is conventionally the most robust description of failure criterion for fracture. Now, you might be tempted to say, well, wouldn't it be nice to just say, let's use our standard descriptions of uniaxial stress strain data. And under those circumstances, rather than plotting everything in terms of force versus deflection, let's express it in terms of engineering stress versus engineering strain, which is really just the same as saying force versus deflection, but we just divide force by the original nominal cross-sectional area of the bar. We divide that kind of end displacement by the nominal gauge length of this bar. And we basically get the same kind of looking diagram. We've just normalized the values of the axes a little bit. However, I want to point out that the area underneath this curve, this engineering strain versus engineering stress curve, is not necessarily a measure of energy, but rather strain energy density. So it's energy per unit of volume in the material. And it fundamentally assumes that the strain energy in the material is the same throughout the entire length of the bar. Nonetheless, if we took data from some uniaxial stress strain curve, we could come up with what is the area under this curve. And it doesn't always have to be a nice linear elastic curve. It could actually involve maybe some nonlinear material behavior. You could do the same procedure to measure what's the area under that curve to compute what's this strain energy associated with the fracture that occurs in the specimen. And then you could figure out what is this fracture energy. If you were measuring it in terms of strain versus stress, however, you'd have to be careful of the units. So rather than taking total strain energy dividing by that cross-sectional area, since this is per unit of volume, we actually have to increase this value by, or multiply it by the actual length of the specimen. So just be careful with the units there. Nonetheless, we could run this same kind of experiment multiple times, and we'd find that the fracture energy is really a quantity that appears to be a material constant. It's a material property that you can go to the laboratory and measure it, and it effectively characterizes, again, that measure of how much energy do I need to put into this material in order to grow the crack by some unit length or something like that. And you can also go to the trouble of saying, well, if I know that this is the criterion for fracture, it's some energy-based criterion that says, if I reach this particular limit, or maybe I even exceed that limit, I know that basically the crack should extend, the crack should grow. So this is my criterion for crack extension, if you like. If I want, I can also define some kind of measure of the strain energy per unit of area at this kind of crack location, and then assess what is this current measure of energy per unit surface area in my specimen, and test, does it exceed this critical limit, this threshold for the critical strain energy or the critical fracture energy. So that's one way that you can assess fracture. But of course, in this simple case where we have linear elastic material behavior, you might be tempted to say, well, couldn't I just specify a stress-based criterion for fracture and just say that, well, I could say that certainly it's driven by the energy in the specimen, but it looks like I could just assess when failure occurs by looking at what's the stress in the material and say this is when fracture occurs. So why couldn't I just say use a stress-based failure criterion to assess when fracture occurs? Well, the trouble arises when we look at not what happens in this overall specimen, but what happens if we look at things from the continuum perspective. Now, I'll invite you to reflect on the fact that this engineering stress measure is sort of a normalized force per unit of area. But it's certainly not representative of localized stresses that might arise in the specimen, let's say in the vicinity of some local defect or maybe some initial crack that might be present in the specimen. And to examine that, consider, let's say, a similar situation where I've taken this bar, I've turned it on its side, and I'm still putting it into a roughly uniform state of tension, at least in this simple kind of one-dimensional case. But imagine that internal to that specimen, there was some small initial crack of length 2a. Just canonically, we'll give it a length 2a. All right, so what's funny about this particular problem is that, in fact, you can come up with an analytical solution to this problem using basic methods of the theory of elasticity. But the weird thing about it is, kind of in analog to the problem of the plate with a circular hole, we do expect that the stress distribution, let's say across this particular cut plane, that the stress distribution is going to be non-uniform. In the case of a plate with a circular hole, the maximum stress occurred right kind of at the center of this defined coordinate system. So right at the edge of the hole in that circular plate. And you'll maybe remember from the previous lecture when we talked about that particular example that the stress concentration factor, or kind of the ratio of this, far field stress value to the value of stress in the local proximity to this, hole in the plate, was roughly a factor of 3 larger than this particular value of the nominal stress. However, in the case of a crack, where basically it's not a circle, but it's just basically a flat kind of line, we can look at what's the stress concentration factor. But unfortunately, it turns out that the stresses in the vicinity of this crack tip location don't actually converge to a finite value. They zoom off to infinity. And that's really a troubling thing, because it implies that there's really no good way to assess when fracture will occur if we're trying to use some kind of stress-based failure criterion, right? Imagine trying to set up a finite element analysis problem of exactly this scenario. You have some kind of plate. It has some initial crack in it. Maybe you mesh the heck out of it even. You put a whole bunch of elements in the local vicinity of this crack tip because there's probably going to be some stress concentrations there. So you want to resolve what are the local stresses there. And you might be tempted to say, well, I can just look at what's the element right next to this crack tip, measure what its value is, and then assess, is the stress in that element close to the crack tip? Does it exceed that critical threshold, that maximum stress at which we said, fracture should occur? But the problem is, theoretically, assuming linear elastic material behavior anyways, which is not quite correct, but assuming you did use this approach, it says that really the stress is just going to go to infinity. And what's worse than that is if you said, okay, well, I just need a finer mesh, right? I'll just use more elements. I'll refine the heck out of it even more. You'll never converge because you're trying to converge to an infinite value. So this is really the troubling thing about trying to define a stress-based failure criterion for fracture. It's really not feasible to do if you're assuming that you're getting away with linear elastic fracture mechanics. So assuming that the material behavior exhibits this kind of asymptotic trend towards an infinite stress in the vicinity of the crack tip. So that's part of the reason why it's not such a great idea to work with purely stress-based measures of failure, especially for fracture, and as you get into these kind of domains. Now, it is true, however, that real materials don't behave like this. A real material can never sustain an infinite stress. So what does it do? Well, it has to undergo some local deformation processes in the vicinity of the crack tip. If you have plasticity, if you have micro scale cracking and damage going on, technically the stresses will plateau at some particular value that's nominally proportional to the yield stress in the material or kind of like some critical threshold. So in practice, the stresses don't actually do this. They do kind of reach some critical threshold value, but it still doesn't tell you anything about whether or not the crack is going to grow, because maybe there is plasticity ahead of the crack tip, but you don't know, has there been enough plastic deformation in order for the crack to advance? And the only way to assess that is, again, to define something that understands how much plasticity has occurred, or in other words, how much energy has been dissipated in this localized zone ahead of the crack tip, sufficient to advance the actual crack. So again, further reinforcing this idea that the proper way to define a criterion for fracture is to define it in terms of some energetic criterion. That in order to grow the crack, we need to have dumped enough energy into this specimen, into this local fracture process zone at the crack tip location in order for enough damage to have accumulated for the crack to grow. So just things to bear in mind, from a mechanistic standpoint, that's kind of the way that we proceed, especially in the finite element context. And, how much energy is required to induce fracture really depends on the type of material you're looking at. You can have very different behaviors depending on the type of material and the mechanisms that they undergo during these different fracture processes. So classically brittle materials that otherwise would do well if we had some kind of equivalent stress-based failure criterion. We could try to use that for these types of materials like glass or ceramics, even to a certain extent, concrete. But at a certain point, as you look at other types of materials, concrete technically falls under this category, as do a few other types of materials. they start to require more and more energy in order for the crack to grow. So the amount of energy we have to dump in for the crack growth to occur starts to increase. And it doesn't look quite so brittle, but it doesn't look so ductile as I would have maybe in a kind of metal. So let's say metals can deform a lot plastically before they ultimately fracture under these ductile fracture mechanisms. So at the left end of the spectrum, I guess from your perspective, we have brittle fracture, where there's basically no permanent deformation or no significant permanent deformation happening throughout, let's say, the specimen. On the opposite end of the spectrum, ductile fracture, not only do we have dissipation happening local at the crack tip, but dissipation is happening due to plasticity and other effects almost throughout the entire specimen, far beyond the region of the crack tip. And then somewhere in between, there's this sweet spot known as quasi-brittle fracture. It's kind of like, there's definitely some non-local dissipation and damage happening in the material close to the crack tip, but it's certainly nowhere near, being characterizable as ductile fracture. So really different mechanisms also govern how these processes evolve. Certainly in concrete or other types of cementitious materials, the mechanisms for how the material separates will look different, at this mesoscale compared to, what it would look like for a metal. So to understand why and how these different things come about, you kind of have to almost delve into the material science and like look at grain micrographs and all that kind of fun stuff to understand why is the crack growing in the way that it grows? Why does it exhibit this dependence on how much energy is being put in there? But yeah, just suffices to say that depending on the material you're looking at, the mechanisms and kind of how much energy it takes to grow the crack will differ pretty substantially. Okay, so coming back to this simple one-dimensional example, I want to point out that if we said, all right, let's try to model this now. Let's say we've taken all this, background and knowledge about how cracks grow in material, and let's actually try to run a finite element analysis that now includes fracture. You get all excited, you go to the drawing board and you say, oh, wait a minute. There was a fundamental assumption that we imposed when we formulated our fundamental theory of elasticity and continuum mechanics. And it hinged critically upon the assumption of compatibility. Compatibility said that if I had some body, elastic body, I subjected it to some deformation, some displacement field, in other words, we imposed certain requirements on that displacement field. We said ahead of time that it had to be a compatible deformation field. Or in other words, we couldn't have splits in the body. We couldn't introduce fractures because that would actually, violate some of the assumptions on which the theory was predicated. So unfortunately, all of the theory that we've come up with now for finite elements assumes that we're working with these so-called continuous or compatible displacement fields. Now, however, if we said, let's come to the theory and try to introduce fracture, we'd be working with displacement fields that are inherently discontinuous. And this is obviously a complication. It basically would require reworking much of the theory in order to accommodate this feature. So this is the fundamental challenge, where there was originally one material point and a continuous displacement field. Now, after fracture, effectively, we had that same point, but basically cleaved in two. So somehow we have to duplicate material points and split them apart and allow for the displacement field to have these discontinuous jumps. So that's definitely a challenge. We'll see what we can do about it. There's a lot of approximate ways that you can deal with this. But in practice, there are two ways that you can deal with this. And the first way is probably the simpler way. You basically say, well, don't do that. Don't actually split the material in half. But do try to make sure that if there is some kind of attempt to have this so-called strong discontinuity in the representation for the displacement field, smooth it out. Make sure that it isn't strictly discontinuous, but instead allow for the displacement field to kind of like ramp up slowly over some finite length. And maybe this finite length, which I'll call this lowercase calligraphic L, represents some characteristic length within which the strain in the material will localize. So imagine I had this bar and I subjected it to that loading, and it, fractures or whatever. What I'll notice is that if I were properly representing this fractured interface as a so-called strong discontinuity or a discontinuity in the displacement field, then I would notice in both halves of this bar, after I've broken it apart, that the strain internal to both halves is just equal to 0. And the strain actually at the discontinuity is just undefined. We don't really know what it is. We just have this discrete jump in the displacement field, so we can't take the derivative of a discontinuous function at that discontinuity location. Conversely, if I said, let's smear out this discontinuity over some characteristic length L, it'd be like saying, well, okay, so strain is going to be 0 in these halves of the bar away from this, localized region. But internal to this region, the strain will have a finite value. It'll be proportional to whatever, extension we've applied to the bar, but normalized by whatever this characteristic length is. So it's sort of like there is a strain here, but it's somewhat fictitiously defined, and it depends on how we've chosen this characteristic length. So really, it's probably more appropriate to be thinking in terms of the displacement jump or the magnitude of how much the material has separated rather than this being a characteristic value of strain. It really does depend on this, characteristic length. But one thing is for certain, we definitely do not want this characteristic length, whatever it is, we do not want it to be dependent on the choice of our mesh. Because if it does depend on the choice of our mesh, then we can continuously refine the mesh more and more and more. And if the mesh size is directly connected to this apparent length scale, then we're never going to converge to anything. So we won't have a well-posed solution in that case. So somehow, if we do this approach of smearing the crack over some kind of finite characteristic length, we have to independently define what this characteristic length is and ensure that it's not dependent on the mesh size. So if we do this, you might think of this particular approach as being representative of a corresponding weak discontinuity, which is really, technically, it's more of a description of a discontinuity in the strain field, where I might have these kinks. So a non-smooth description of displacements, but nonetheless, the displacement field is continuous. So if we do this kind of smeared cracking kind of approach, then we can still get away with using our classical theory of finite elements and try to apply everything in that context without having to do any extra work to rework the theory and try to include these strong discontinuities. Nonetheless, there are ways that you can include strong discontinuities, but we'll have to reserve some of that discussion perhaps for a little bit later. Okay, so with that in mind, there being these two alternative ways that we can represent fracture, either in this smooth, kind of like smeared sense, or in this discrete sense, as strong or weak discontinuities, really that classifies two broad categories of fracture modeling approaches as you might encounter in the literature. So on the left, we have discrete crack models. These are, actually trying to represent that strong discontinuity or a jump in the displacement field. And one particular example, one of many possible different modeling strategies for including strong discontinuities in the solution field, is this so-called cohesive zone modeling approach. It's kind of like we say that, at some interior interface, we insert a bunch of interface springs, if you like, that hold the interface together up until the point of fracture. And then once they exceed some critical threshold, then those springs kind of break apart. So it's kind of like you have to introduce these inter-element interfaces represented by these so-called cohesive zone elements or cohesive zone models, which are really nothing more than a fancy word for a bunch of springs. So just put a bunch of springs into your mesh that kind of lose their stiffness as you pull the material apart. Yeah, simple enough. And in that way, you can kind of emulate the behavior of fracture. The other way, smeared crack models, effectively, can be classified into a bunch of different categories. There are a bunch of different alternative ways you can do this, but probably the most common one that you would encounter is this so-called continuum damage approach, where you just take a regular constitutive model, kind of like the ones that we've been considering up to now, and you just say that it includes some strain softening behavior. So whatever the slope of the stress strain diagram is, if it has a negative slope at a certain point, That you assume that that is representative of some kind of localized damage or even fracture in a certain case. But you do have to do some special things to make sure that you get consistent results and that you don't get artificial dependence on the choice of your mesh. So going through a couple of these, we'll talk first about these cohesive zone models. All right, and as I said, it's basically like you're taking a bunch of springs and you're inserting them into the inter-element interfaces in the mesh. So that's one way that you can include these different cohesive zone models. There are more fancy ways that you can, choose to introduce these interfaces. Rather than introducing them at the boundaries of inter-element interfaces, more complicated methods will actually cut the elements apart. They'll take the elements and then just cut them in half or introduce some kind of strong discontinuity, and you're permanently changing the actual displacement fields that you're using to interpolate the solution at that point. So where I might have had originally one node, let's say, that connected these two elements together, I would actually have to duplicate that node and now have two independent degrees of freedom that can displace independent of one another. Nonetheless, they have to be connected by this, cohesive zone, or a fancy word for a spring that I put in here. And I can define some kind of nonlinear relationship for how that spring behaves as it gets stretched more and more open. So initially, prior to any fracture, I can assume that all the nodes of this mesh at all the inter-element interfaces are connected together. And after it reaches maybe some critical threshold, perhaps even driven by or kind of seeded by some kind of stress-based criterion for when this begins, I can say, oh, I've reached some critical tensile stress threshold along this interface. And I know at that point, I need to insert one of these so-called cohesive zone elements. It's kind of like this element consists of two faces paired together, where those two faces were previously one face in an inter-element interface between two solid elements in the mesh. And once I insert this cohesive zone, I basically have to measure what's the relative displacement jump across this interface between these two surfaces. And from this description of this kind of displacement jump between those two interfaces, I can measure what's the relative traction or the normal stress across this interface as a function of this opening gap displacement. So it's kind of like this spring or the extension of this spring, which initially has 0 length, which I'll denote its displacement or relative displacement as this lowercase delta symbol. This displacement governs effectively how much this traction will have to degrade over, continual opening as the crack continues to grow. And you'll notice that technically speaking, there could be multiple of these elements, encompassing the fracture process zone. So it really takes time. As you kind of open this crack, it's not just that you split the elements apart and then that's your new fractured interface. Really, you split them apart, but then you insert these springs and allow the springs to continue to extend, but to lose stiffness over time. So it's kind of like you have to define an additional constitutive model, but specialized to the case of this so-called traction displacement kind of relationship. So you define a relationship between this opening displacement and the resulting traction that occurs in this interface and allow it to degrade as you continue to open this interface. And the nice thing about these traction displacement models is that precisely the area underneath this traction displacement curve is nothing more than the fracture energy, or basically the energy per unit of surface area required to fully separate those two surfaces. So as soon as I've kind of extended the crack or kind of opened the crack wide enough, I'll have dissipated all of that fracture energy associated with that surface. And now I'll say that truly a fracture has occurred, that a crack has kind of extended into this element. So that's kind of the simple way to interpret these cohesive zone models. They're just kind of, they require introducing these inter-element interfaces into the mesh, and they require defining this traction separation relationship, a constitutive model that governs this kind of amount of traction applied at the interface to try to hold the crack closed as a function of the crack opening displacement. It's not unlike a penalty-based contact formulation. In the same way that, interpenetration of the contacting interfaces, it could be modeled as including these, contact springs to try to push them apart. Now these cohesive models really do the opposite. They try to hold the crack closed, but they lose stiffness, obviously, as you continue to pull the surfaces apart. So that's cohesive zone models in a nutshell. And then the other major one is continuum damage models. And this is really kind of an analog to that same approach. We want to try to emulate that behavior. We want to dissipate energy, which means that the stress, not in the interface, but the stress in this solid region of material also has to degrade or lose stiffness as we continue to try to advance the crack. So rather than actually representing a discrete crack, though, we treat it as being smeared over this kind of patch of elements that encompasses nominally the fracture process zone. So kind of similar approach, but we just suppose that everything is being smeared out over the interior of one of these solid elements. And the nice thing about this is obviously, well, all we need to do is define a regular constitutive model that exhibits this strain softening damage kind of relationship. So as long as I kind of include damage in this strain softening model for whatever my material behavior is, I kind of get the same behavior, more or less. The one caveat, though, is that the area under this curve, not a traction displacement curve, now it's a stress versus strain curve. The area under this curve is not equal to the fracture energy. You actually have to normalize it by some length scale in order to get the right units. And that length scale that should be used ideally is actually proportional to the element size, because you're normalizing the displacement jump by this kind of width of the element. So when you do this, it basically means that you'll get a different looking stress strain curve depending on this value of H. So as you shrink the elements more and more, H will decrease, and the apparent strain energy or strain energy density under this curve will look like it's continually increasing, which is kind of a paradoxical thing, but there are continuum damage models that take that kind of thing into account and include this dependence on H, which you might think and say, well, isn't that introducing an artificial dependence on the element's size? Well, yes, but the important thing is that we're getting the energy right. If we didn't normalize by this length scale corresponding to the element's dimension, then it would kind of look like the energy dissipated due to fracture in the limit as we kind of make the mesh smaller and smaller would kind of like almost tend to zero, which makes no sense. It would make it seem like it's really easy to generate a crack if we refine our mesh. So we absolutely need to include this in order to ensure we're dissipating the right fracture energy. So that's kind of a nuance. But with both of these approaches, the cohesive zone model approach, as well as this continuum damage modeling approach, it's worth pointing out that there's a huge dependence on how you've chosen to mesh these problems. In the case of cohesive zone models, how you've designed the mesh and how the edges of the mesh are oriented will govern how those cracks tend to extend through the body. There will be, in other words, a bias as to how the crack will grow depending on the orientation of the grid lines of the mesh. And that makes no sense at all. That's why those kind of methods for cutting the elements in half are actually, preferred in some cases in order to eliminate that mesh bias in predicting what's the direction or orientation at which the crack will grow. The same kinds of issues show up for continuum damage models, by the way. There are specialized, treatments that you can do to try to get rid of that phenomenon, but it's still a problem. And honestly, it makes it more complicated. Besides the fact that continuum damage models have a bunch of other issues to deal with. In short, continuum damage models, even though they provide an appealing alternative, generally speaking, they don't really predict crack growth direction very well. And there's a bunch of other issues that they encounter. So just be cautious when you use these types of approaches. Now, the last one that I'll point out is something called, it has various names. Some people call it element deletion. Some call it element erosion. I'm personally partial to element death because it's kind of like the elements at a certain point when they reach some critical value of maybe it's stress, but maybe it's something else. You just delete them. You get rid of them. Sometimes that's a bit of an approximation, but sometimes that's the only tool that you have at your disposal. And in general, element deletion is not a great option if these elements were otherwise carrying some amount of stress, because you kind of want those elements to dissipate all of that fracture energy, right? If you just said, oh, it reached this critical stress threshold, delete those elements, you'd be getting the fracture energy wrong. You need to at least have dissipated the correct fracture energy before you delete these things. And it turns out that one way that you can ensure that you do that correctly is in the case of not brittle materials or even quasi-brittles, but more so for the case of ductile materials, things like metals and plasticity and steel and things like that. It turns out you could use an energy-based failure criterion, which is proportional to saying take the area under this stress strain curve. But almost equivalently, you could say, relate that energy or this area under this curve to the apparent plastic strain that's accumulated in the material. So for a lot of materials, it's sufficient to just say that there is some critical plastic strain or equivalent plastic strain at which the fracture in the material will occur due to some kind of ductile failure mechanism. So if that's the case, then I can use this element deletion criterion that says once the plastic strain in some, just simple plasticity model, once it reaches this critical threshold, just delete the element. And it's kind of like I'm almost doing ductile fracture. It's kind of a hack, but it still works surprisingly well given how much of a hack it is. So just be cautious, if you're using element deletion, there are other reasons why element deletion can help you. Obviously, if the elements are really getting distorted or becoming a problem in your analysis, there are occasions where it's actually useful to just delete them just to make sure that they don't become a huge problem. But otherwise, it's also kind of a method of last resort if you're trying to model things like fracture. But it works okay, at least if you're doing ductile fracture. Okay. The main thing that I'll point out, which I kind of briefly touched on in the case of continuum damage models, is that you do get significant dependence of your solution on the choice of mesh that you're using. So if I chose to discretize this uniaxial bar example from before with one element or three elements or 5 or 7, and I tried to use a continuum damage modeling approach, what I'd find is that obviously, depending on how many elements I'm using, the weakest element in this chain of elements is the one that's actually going to experience this localized fracture. And unfortunately, this is really, you might say, well, it's converging, right? It's converging to there being this kind of localized zone in which fracture will occur. Well, that would be nice, but unfortunately, it's really not your answers will still be sensitive to the choice of your mesh. So this is unfortunately the consequence of trying to use these continuum damage approaches. And there are specialized ways that you can deal with this. Sometimes people have developed things like non-local damage models to try to deal with this. There's phase field models of fracture, which is a slightly different approach, gradient inelastic damage models and things like that. Try to address this problem and make sure that, if you get below a certain number of elements, then you'll still kind of converge to the same answer, but it requires smearing out the damage over some kind of zone of elements rather than having the damage localized into just the single smallest element and the weakest element in these cases. So just be really careful when you're using these types of strain softening constitutive models to try to emulate fracture. You're not going to converge to a unique solution unless you use some of these specialized approaches. All right, the last one, I won't have time to show it to you, but I'll invite you to go and play around with it, is yet another kind of interactive simulation tool that looks at cohesive zones. So I'll invite you to take a look at it at your leisure. The links are provided here if you want to take a look at it. Otherwise, I'll have to look forward to your presentations on Monday. And thank you all for your attention throughout this whole semester. I've very much enjoyed having you all here. So with that, I'll conclude and let you get on with your day. All right, thank you.